transformer may have the same voltage rating. They even may have the same power rating. For example, transformer 1 and transformer 2 both are 2 MVA transformer, but technically they are not same. And that's why it is important for us to understand what is the differentiation between these two transformer. And how do you know that? Of course, by watching this video, because in this video I'm going to break down the 5 such important parameters of the transformer that will help you identify if the two transformers are same and can you make the parallel operation out of this. In fact, the last parameter that we will discuss will have direct impact on the short circuit level of the system. So let us start with the first parameter. The first parameter is the vector group. Now you would have generally seen some kind of coding like DYN11 or YND1 and things like that. Now certainly these are not the random numbers, they have the meaning with it. Of course, we need to know what is the type of primary winding, what is the type of secondary winding, do we have neutral available or not, and all those things. And basically, this vector groups tells us that exact thing in, of course, a code format. The only thing is we need to decode these codes, right? So do not worry, I'll help you understand what do they mean. So let us understand what is the meaning of each and every letter, the number that you see here. The capital letter represents the HV winding connection. Whether the HV winding is connected in delta or it is connected in star, that you will get from the capital letter. So D means delta and Y means the star connection, only if it's in the capital. Then all the letters that you see in the small represents the LV winding connection. Again, D or Y depending on the type of connection. Then N or small n indicates the neutral is bought out or not. So you need to know whether you have neutral available on the transformer, that you will get from here. So is it available on the primary side? Is it available on the secondary side? Or is it available on the both? That information can also be noted down from the vector group. And then the numbers that you see, like in our case 11, represents the phase displacement using the clock method. So we use that clock method. That's the standardized practice in the industry. So every hour on the clock represents 30-degree phase shift between HV and LV winding. So when we say 11, so 11 divided or 11 into 30 will give you 330 degrees. That's the lagging, or you can say 30-degree lagging, right? So that is the meaning of that number. So this is very crucial. It gives you the type of HV winding, LV winding, then it gives you neutral information on what is the phase displacement. So let us decode the number that you see on the screen, and that is the number you will most commonly find on the distribution side of that. So here the D indicates HV winding is delta connected. That means we will not have neutral, because in delta connection we don't get neutral. Neutral is available only in star connection. By the way, if you're interested in knowing what is the difference between star and delta connection, I have a dedicated video on that. I'll put a link for it down in the description. Definitely go and check that out after this video. Then we have Y, that indicates the LV winding is star connected. And there we have also taken out neutral. And this is something necessary when we talk about the distribution side, because distribution sides loads are mostly not balanced, and there you need neutral. That's very crucial. And then the 11 represents 30-degree phase shift, leading phase shift, or 330 degrees lagging phase shift. So that's the very important information you need to know. And this vector group can differentiate the transformer even if they have same voltage rating, they have same kVA or MVA rating, right? When you have to do parallel operation of the two transformer, you have to make sure that they share the same vector group. If you connect two transformer with two different vector groups, then there can be problems, losses, heating, and a lot of other things. So that is something must be avoided. And to avoid that, the first thing very important is to understand the vector groups, right? So that is the first parameter, very important for you to understand. And another important thing is, of course, subscribing to the channel, because that's how you'll get updates on the next upcoming videos. Now let's move on and talk about the transformer losses. This is very crucial. Now we know transformer is an efficient machine, but still they are not 100% efficient. There are losses, and this will be true for every electrical machines, every electrical things that you will see. Nothing is perfect. Everything has losses, and certainly transformer is also no exception for that. And this is very important for you to understand the losses, because if you choose a wrong kind of losses or wrong kind of design for the application, the whole application will suffer, right? So let us understand that. Now transformer has two major types of losses: the core losses and the copper losses. Core losses are also known as the iron losses, and they are dependent on the core of the transformer, and they are fixed in the nature. This is also called as the fixed losses. So irrespective of the fact that whether you have connected some load on that transformer or not, but if it is energized with the frequency and voltage, the core losses will happen in the transformer, right? And that's why they are also called as fixed losses. The on core losses, the load has no impact. It really doesn't matter if you're consuming 50% of load or 100% of load, the core losses remains constant. And in core losses, we have hysteresis and eddy current loss. And then we also have copper losses, which are also known as the variable losses, because they will vary based on the loading on the transformer. If the current increases, the copper losses also increases. If current reduces, the copper losses also reduces. Now you need to understand the impact of these losses. Imagine a situation, let's say you have a factory, and the factory runs only for 8 hours in a day. So 8 hour you will have maximum loading on the transformer, but balance or the night, the evening, there is no much loading. In that case, if you choose a transformer with high core losses, you are going to incur losses even though your transformer is not loaded. And then that may be the wrong choice in that case. You will have to focus on the transformer which offers lesser core losses. The same thing is also true for copper losses. If your transformer is always loaded at 80-90%, you need to choose the transformer which will have less copper losses. This is something true for utilities. Most of them are loaded power transformer. Most of the time they are loaded at the maximum available limit. So there they need to choose the transformer which has less copper losses. If you do not pay attention to that, then for sure the application will suffer. The transformer will incur more and more losses. Now initially maybe the cost of transformer with less losses will be high, but that becomes a better choice if we look at the future. If you buy a cheaper transformer with higher losses, ultimately you are going to pay a lot of money because it's going to incur a lot of losses. So that's why it's very important that you understand the losses and what impacts them. Right now, I have done a dedicated course on the transformer theory. It's a basic level course which talks about the ideal transformer, the practical transformer, transformer on load, transformer on no load. Everything is explained in that. It's a very basic level course and beginner friendly. If you're interested, I'll put link for that course down in the description. Definitely go and check that out. Right, so those are transformer losses, which takes us to the third parameter, which is tap changers. Now transformers are a great invention, no doubt about that, but the voltage in the power system does not remain constant. It will change based on the loading and lot of other stuff. Reactive power in the system, that is also something contributes to the voltage regulation. So the transformer can also help us in managing that voltage regulation, right? So imagine you are sending 420 kilovolt to one substation, but that substation is receiving 550 kilovolts or only 300 kilovolts, right? So that is something not acceptable. The devices will not appreciate that, right? So to manage that thing, to manage the voltage levels, transformers are also provided with the tap changers. The logic here is simple: the transformation ratio, which if you see here, which says the secondary voltage depend on the primary voltage, or it depends on the number of primary and secondary turns. So any of these things, if you change, the secondary output will change. Of course, the primary side voltage we cannot change. So what we can change is we can adjust the number of turns on the secondary side or number of turns on the primary side, and we can adjust the voltage without touching the generating stations. And this becomes really, really useful in power system. And that's why you will find transformers are provided with tap changers. The taps are adjusted so that we match the output voltage level, the voltage that we want, right? Now these taps can be provided on the primary side, can be provided on the secondary side, depending on for what application you are using it. And there are two types of tap changers available: the offload tap changing and the on-load tap changing. Offload tap changing, of course, as the name suggests, you need to change the taps manually and by taking full shutdown. It cannot be done when the supply is on. So here is an example. You simply turn the knob and the voltage output will change. Now the steps you need to see on the transformer, is it 2%, 3%, 5%? That will vary manufacturer to manufacturer and project to project. Now the problem with this is it needs complete shutdown. So the transformer must be completely isolated in order to do that, and it's fully manual, and there is no real-time control. But we do also have on-load tap changers, that is also called as OLTC. And this goes and fits directly inside the transformer, and the tap can be changed automatically based on the voltage condition. If voltage is dropping, the taps will be changed automatically and will bring back to the normal voltage levels. But of course this will be expensive compared to the offload tap changers. But if the application is critical, this makes more sense, and this needs to be maintained well. If not, this is one of the major reason why transformer failure also occurs. So that is something you need to keep in mind. So you need to see whether the transformer is capable of also providing the voltage regulation. If yes, is it the offload or is it the onload? And what is the percentage setting for that? So that information you will find on the transformer details, which takes us to the fourth parameter, very important one, the cooling method. See, transformer is good only if it is within the specified temperature limit. If it goes beyond that, the transformer will lose its life very quickly. And cooling method are the thing that will keep your transformer cool within the specified temperature limit, so that it can work as defined by the manufacturer. So cooling is not just about the comfort. Cooling will directly affect the type of life of the transformer. And the 10% increase in the temperature can reduce the life of any equipment by 50%. So this is something crucial, and that is something paid a very detailed attention in transformer, right? And when you look at the nameplate of the transformer, you will generally find some codes like ONAN, ONAF, OFAF, OFWF. Now these are different types of cooling methods used for that particular transformer. These are again the short forms. I'll explain you what they mean. So ONAN is basically the oil natural air natural cooling. So in this case, the oil inside the transformer flows naturally. Air also flows through radiators naturally. We are not putting any fans, we are not putting any pumps for the oil. So this is something used for the low power transformers, and maybe something which is put inside the controlled environmental conditions. So there it can be useful. The ONAF is basically oil natural and air forced. So oil again moving naturally, we are not touching that part, but air, we are using fans to make air flow through that, right? So this can be used for mid-level power transformers. Sometimes you will also find two ratings defined. So I will say, let's say 20 MVA with ONAN and 25 MVA with ONAF. So if I'm not turning on the fan, I can use up to 20 MVA loading. But if I want to increase the loading, I need to turn on the fan, and the transformer will be able to deliver 25 MVA without any problem. So that dual rating also you may find on the transformer. OFAF is oil forced and air forced. So here we are not depending on the natural flow of oil. We are using pumps to circulate the oil and take out the heat from the transformer winding. The same way we also have oil forced and water forced. So Here we are using water to support take out the heat from the transformer. This is used for high or heavy loaded transformer, or the higher power capacity transformer. If you know anything else, please do let us know that via comments. Now, cooling is very important, and this is something very important for you to understand, because transformer may have staging control. So when the transformer reaches to a certain level, the first set of fans will start. When it goes beyond that, the second set of fans may start, and when it goes beyond that, even it may cause an alarm or even tripping action. So there are indicators provided for winding temperature, the transformer temperature, and everything, right? So cooling is something very, very important. It's not about the comfort, it's about the life of the transformer. So this is something you must pay attention to, right? Which takes us to the final and the very important parameter, the impedance of the transformer. Now, this is something will directly contribute to the short circuit level of the system. And this is generally you will find on the nameplate of transformer mentioned in terms of percentage, like 5%, 6%, 10, 12%, like that. Now, in simple language, impedance is basically the resistance in AC circuit. Now, we cannot use the word resistance in AC circuit because impedance is a comprehensive term. It covers all the oppositions we have in the AC. So we have capacitive reactance, inductive reactance, resistance. So everything put together, what we get is impedance, right? And impedance, why it is important? Because it directly impact the short circuit current. So imagine if there is a short circuit on the secondary side, and the impedance of the transformer is less, 2%. Now, in that case, the short circuit current will be very high because the opposition to that current is very low. Another case, short circuit happens, but the impedance of the transformer is 20%. In that case, the short circuit current will be much lower compared to the previous case. Now, you will say, okay, if that is the case, I'll go and choose the transformer with high impedance. Well, that's not again the right choice, because impedance also impacts the voltage drop. Higher impedance will have higher voltage drop, and the poor regulations because of that. So you cannot go and choose higher impedance transformer. Now it boils down to the balance. You have to find out the balance between how much voltage drop you can accept and how much short circuit current you can accept, right? And that's why this parameter becomes really, really important while selecting the transformer, because all the devices that you will be connecting next to it, let's say the circuit breaker, the disconnectors, and everything, must be capable of carrying that short circuit current for specified amount of time. And circuit breaker should be selected according to this, should be able to break that short circuit current. So this is something really, really crucial when we talk about transformers. So those are the top 5 parameters that we talked about. Now let us quickly summarize what we discussed. First, we discussed about the vector group. That is very important because it will tell you how the HV winding is connected, LV winding is connected, where the neutral is provided, and what is the phase displacement. Then we talked about the transformer losses, which is contributed by the core losses, which is the fixed loss, and the copper losses, which is the variable loss. You need to select this thing based on the application of the transformer. Then we discussed the very important thing, that is tap changes. It can be offload, it can be onload. This is very important to have a balanced voltage in the power system, and many transformers are supplied with the tap changes. Then we discussed about something that directly impacts the life of the transformer, the cooling methodology. It depends on the application and the capacity of the transformer, but understanding that is very crucial. Then finally, we talked about the transformer impedance, which can directly contribute to the short circuit fault, and you need to find out the balance between the voltage drop that you can accept and the short circuit level that you can handle. So those are top 5 parameters. I hope you are clear with that, and with this understanding you will be able to understand whether the two transformers, even though they share the same voltage rating and the MVA and KVA rating, are they really same or not, and whether you can do a parallel operation of the transformers or not, right? I hope this helps, and if you're interested, as I said, I have a dedicated course talking on the transformer basics, beginner friendly. The link is in the description. I'll also provide link for the YouTube playlist that I have on Transformer. Definitely check that out for more details. Thank you so much for watching, guys. I'll see you in the next one. But till then, keep watching, keep learning.